All right, so our next session is session 2, Rio Grande, Silvery Minnow, Life History and Biology. Mo Hobbs from the Water Utility Authority is going to be moderating that. Mo, I just made you a co-host, so you will be able to unmute now.
Perfect. Can you hear me now?
Yes.
Awesome. Okay, thank you so much for that lovely presentation and tour. I've never gotten a chance to see it, but I lived in Roswell for quite some time, so that was nice to see. So our next session is Rio Grande Silvery Minnow, Life History and Biology. Just a few reminders for anyone who just joined us. We are going to be taking questions in the chat, and then if we have time, the presenter will be able to address those questions, and any questions that we don't have time for, they will be sent to the presenter and addressed. Awesome.
And just as also a reminder, the agenda with all the abstracts are available on the program portal. I'll stick the URL in the chat again, so those who don't have it already can follow along.
Awesome, thanks Debbie. And so up first in our session, we have Robert Dudley with the American Southwest Ichthyological Researchers and Museum of Southwestern Biology at the University of New Mexico. And his presentation today is Rio Grande Silvery Minnow Reproductive Monitoring, 2003 to 2020. So we'll give them a second to get that loaded up.
Okay, great. Thanks, Mo, for the introduction there, and I'll get the screen sharing here. Okay, good morning. My name is Robert Dudley, and I've been studying the ecology of native fishes throughout the American Southwest since 1993. I went on to do my master's at Arizona and doctoral program at UNM. Currently working as a freshwater fish ecologist at ACER and also an adjunct assistant professor at UNM. So what we're talking about today is the long-term systematic monitoring of the reproductive ecology of Rio Grande silvery minnow. This project started in 2003, and I'd like to just acknowledge my co-authors as well. Tesha Robbins and Stephen Platania, also of ACER, and Gary White, who's a professor at Colorado State University. So here's a picture of Rio Grande silvery minnow. Just a beautiful photograph here from Tom Kennedy. You can really see the colorations there. Wonderful little fish. It was listed as federally endangered in 1994. And here is a photograph of the eggs. So these are really remarkable eggs. They're really unique. Of all the freshwater fishes in North America, somewhere around 1,200, only a few, and Rio Grande silvery minnow being one of them, have these eggs, and they're just incredible. They have they're non-adhesive, and they're almost neutrally buoyant, which means that even just wisps of river currents can disperse these eggs into different habitats. And depending on flow conditions and habitat, they can either be largely retained upstream or can be dispersed widely in long distances downstream. Historically, there were a number of species throughout the Rio Grande Basin, Rio Grande silvery minnow being one, and here's the rest of the reproductive guild. They were widespread and abundant. In some of the old historical surveys, they would make up 80–90% of the total catch at a particular site. But subsequent to a lot of development within the area, building of dams, and then the dams led to changes in river flow conditions. So the flow regimes changed. And when the flow regimes changed, and along with the sediment, it led to degradation of the habitats and disconnection of the floodplain. Talk about that a little bit later. The only one left, though, with drifting eggs in New Mexico is Rio Grande silvery minnow. So it's a special little guy. So here we are with looking at the study area for this particular project. We've got 3 sites, and they're all located just above these areas of interest. So, you know, they're above diversion dams, or in the case of our lowest site, above Elephant Butte. And so really what we're doing with this project is we're looking at the downstream transport of these eggs just before they get to these structures. And how do we do it? So we've got these collection devices called more egg collectors. Here we show some people out in the river. We've got stands to make the sampling safe. And we measure the volume of the water. We also take temperature at a regular time interval. And the sampling is intense, 4 hours a day at each of these sites, and it goes on for 50 days. And we measure all sorts of things, including the presence of the eggs, the number, the volume of water that was sampled, which enables us to look at things like the density. And we can also look at this. This is really based on the discharge at the nearest gauging station. So what were our objectives for doing all this? Characterize the timing, duration, frequency, and magnitude of spawning. Second, to look at how these things interrelate. So flow, temperature, and silvery minnow occurrence within years, and then also what's the influence of seasonal flow on egg occurrence and passage rate across years. So here's a nice schematic, and it kind of gives us some, over the last 2 decades, what we found. These eggs are generally spawned from about mid-April to mid-June. And it coincides with the most important thing, and we'll be talking about this a lot throughout these sessions. This is where it all happens. So this is the flow, the annual flow, the snowmelt that comes down, activates the floodplain, peak flows, things recede. And meanwhile, these fish are spawning, the larvae are developing, and eventually the juvenile stages come on later in the summer. So this is around the time when the water temperatures are about peaking. So they peak a little later than the flows peak. And here's just a general schematic of a year, 2012 at San Marcial. And so what we see is happening is egg densities shoot up dramatically, orders of magnitude. So going from 1 egg per 100 cubic meters up to nearly 1,000. And they're coinciding with the flow. But also you notice it's a little at the little cooler end for the water temperatures. So we have that going on. But we also have some issues here that we have to deal with from the data standpoint, which is the data are all over the place. So ranging across orders of magnitude, and a lot of zero data as well. A lot of days where we just don't catch anything. And so what we need to do is consider that to be able to analyze those data, we need to do something else. Here we have just a schematic showing the passage rate, so eggs per second, lots of zeros, as I said, and then just kind of this long tail. We don't want that. What we want is something that looks more like this for parametric data analysis, the classic normal curve. And so what we need to do is transform these data, and we use what's called a mixture model. And we'll talk about this more later because it kind of figures into everything. There's a logistic model for occurrence, and that's just using presence absence. So it's just ones and zeros. You can kind of figure out the occurrence probability based on just the ones and zeros. And then we take the zeros out because they cause all sorts of problems when you try to put them into a normal model. And we can analyze just the presence data using a log normal model. So 2 symbols here that we'll come back to: delta, showing occurrence, mu being the passage rate. And those, and you can see them right here, they fit into this equation and allows us to compute the overall passage rate using all available data and including the variance of the log normal relationship as well. And we can calculate the confidence intervals around those values as well. And that gives us the ability to look at these patterns over time. So here we have the main relationships across all 3 sites, looking again at these eggs per second. As I mentioned before, spawning periodicity is generally late April through early June. The passage rates are highest in these lower these lower areas like Sevietta and San Marcial, consistently higher than Albuquerque. Also the passage rates trends. They're generally similar across sites, but we have an anomaly in 2020. Things were very high at the 2 upstream sites, very low at the downstream. I'll come back to that later. So this is kind of part of our second objective. So we're looking at egg occurrence, and we're looking at it within years, and the pattern that we're interested in here is looking at how this occurrence probability changes as a function of the discharge. So how much flow changes across days. And what's remarkable here is that it doesn't matter if it goes from 50 to 100, 500 to 1,000, they respond to this flow very dramatically. They spawn, and we find a very high occurrence probability when these flows change dramatically over a day or two. Not quite as dramatic, but also interesting. We do find that this occurrence probability, so the frequency of spawning by these guys during these, across the course of a year, more so at the cooler water. So this would be earlier in May versus later in June. And that's what this is illustrating. So this kind of brings us to the core. So this is the third objective. And what this shows, this is the long-term pattern of these eggs passage rates versus discharge across time. And what we find is very curious. Very high levels of egg passage rates during low water years, and lower in general passage rates during the high water years. You can just see that visually. Now it breaks down in 2020. So kind of the opposite. And what we think's going on here in 2020 is that we had a series of rainstorms. We had essentially no spring runoff, but we had a series of rainstorms. And they affected the upper 2 reaches, and the fish spawned really high numbers. But in the lowest reaches, the water never arrived. And the highest flows were around 60 or so CFS, just a small, minute fraction, as you can see, compared to other years. And what we think is going on here is just a complete reproductive failure in the lowest reach. And now what we can see is the two, if I break these apart now, we're going to look at the ecology a little bit. We want to look at mu and delta separately. So we can break these apart and we can see what's the frequency of spawning, that's the delta, and then what's the magnitude, so we're measuring that by the mu. And more or less they track each other, but there's some differences, and so that allows us to tease these apart in the analysis. So here's the analytical framework that we used for this project. Generalized linear models, they included both of these parameters, and we used a single environmental covariate for each parameter. You can see just some examples here. We used 6 covariates, and they really just represented the spring runoff conditions that are going to be most affecting silvery minnow during this time. Floodplain inundation as well, we added this year, 2020. We also looked at the fixed effects, which probably everyone's familiar with. It's just a straight relationship. We also added random effects, and that adds a little bit of wiggle room, if you will, around some of these environmental covariates, because we have uncertainty. We're not sure about either the absolute numbers of these eggs or the absolute flow that was at a particular gauge on a particular day. And then we use standard methods to evaluate these different models. So goodness of fit tests, log likelihood, and AIC, assessing the fit of the data to the various models. Okay, so here's what it looks like by itself. So we've got this estimates of our EX now, eggs per second. We're looking at different flow covariates, maximum flow, number of days above a certain flow threshold, inundation of floodplain habitats and mean flow. And you see something very interesting here, which is at the lower ends of all these, we have quite a bit of variance. There's a lot of spread from high to low. So 2020 being the red, you can see the reproductive failure there. Other years though, with these really low flows, you get some of the highest values for EX. Whereas if you move farther to the right on all these graphs, you kind of start to lose that. And it gets pretty dramatic on some of them, where you just have a complete absence of data at those high flow years. So we'll talk about what that means. But here's the main models. And so the top three taking the majority of the weight on all these. We have delta, corresponding closest, so explaining most of the variation, was this covariate that's a number of days above 2,500 CFS. And then for our magnitude, we have the maximum flow in this reach was explaining most of the variation in our magnitude of egg collections. So another way to say this, and we'll wrap things up here, egg occurrence probabilities highest during years with the lowest flows, truncated spring flows, whereas these passage rates, they were lowest during the years with the most elevated and highest spring flows. And what that means is, what we're seeming to be pulling and teasing out of these data is a pretty constant pattern. That's this upstream retention and recruitment of these fish. It's positively related to this availability and persistence. So it can't just be there. It has to last probably about a month to get these fish out of the vulnerable larval stages. And that's best during these high spring runoff years. So coming back to the main issues that we're trying to solve, reconnecting fragmented reaches, reestablishing dynamic river flows, and then probably most importantly, restoring this functional floodplain. That's crucial, regardless of the flows. And in terms of long-term recovery, tying all these things back, it can't just be a mechanical solution. It has to happen over each year. And so they need these flow conditions to occur for this reproduction to happen, for the recruitment to be successful. It has to happen each year. So with that, I'd like to just wrap things up. These are the folks that help with the project. Thanks everyone today for your attention. And if we have time for questions, we'll do it now, or we can do it later. Leave that up to the hosts. Thank you so much.
Thank you so much, Rob. I'll give people just a second to see if we have any questions. Currently, I don't see any questions, so I know it takes a little bit longer, so I'll give people a second and I'll go ahead and introduce our next speaker. We have Thomas Archdeacon with the U.S. Fish and Wildlife Service, and this is going to be a pre-recorded presentation, so Michelle will be uploading that, and then Thomas will be available for questions. So Rob, I'm not seeing any questions come through, so, oh, we got one right at the last second before I spoke too soon. So our first question is from Thomas Archdeacon. He says, "Hi Rob, thanks for the excellent presentation. A lot of this looks fairly consistent with your 2007 paper on particle drift. Can you elaborate on anything you've learned since then?"
Yeah, so it does tie in very well with our past findings. The thing that's probably most interesting that we've learned over the last 13 years since the publication of that paper is just the importance of these floodplain habitats. Within the paper, we kind of elaborated on the importance of habitat. And by doing this study, what we've found is that habitat is really the kind of the crucial factor here in determining how many of these fish eggs drift downstream. So the real question at the moment is, what can be done during these lower flow years? Can there be any sort of reconnection of the river to the floodplain? Could that help with retaining some of these eggs? Because those are the years that things really seem to break down. Is not only do you have low flows, the fish are spawning, but then the eggs just aren't being retained. They're being essentially flushed past these diversion dams or into Elephant Butte.
Thank you so much, Rob. We do have another question, but we're about almost 5 minutes over. So I'm going to go ahead and turn it to the next presentation and we'll get you those questions submitted. So thank you so much.
Perfect. Thank you.
Yeah.